Hi student, this is the second class on electrostatic potential, and here we want to find out electric potential at an external and internal point of a hollow charged spherical body. Can you remember during the study of Gauss's law, we calculate electric field intensity at an external point of a hollow charged body. I think you can remember it. We find out electric field intensity at an external point of a hollow charged spherical body. Or in that case, what we get the expression E is equal to 1 by 4 pi epsilon 0 Q by R squared. Is not it? We are getting that expression already. Yes or no? Or in that expression, we assume that our expression, from that expression, we can assume that the entire charge is supposed to be concentrated at the center. Yes or no? So if we apply that particular concept, this charge is supposed to be concentrated at the center of the charged body, and the observing point is at a distance r, then what is potential at that point? Q by r, 1 by 4 pi epsilon 0 Q by r. What is potential at the surface? Again, the entire charge is supposed to be concentrated at the center. This distance is capital R from here to here. What is potential at the surface? Vs is 1 by 4 pi epsilon 0 Q by r. But what is potential at internal point? But what is intensity at the internal point? Can you remember? Intensity at internal point found to be 0. Right? So A2 more ki asil. This is the more charged body asil. A2 charged body asil. A2 internal point asil. We consider the Gaussian surface here. What is the electric flux associated with it? Electric flux associated with Gaussian surface আমি কিমান পাইছিলো? এইটো সোয়া E into 4 pi r square. তাৰপিছত আছিল কি? Total flux is equal to 1 by epsilon 0, total charge enclosed by the Gaussian surface. What is total charge enclosed by the Gaussian surface? This Gaussian surface encloses no charge at all. Therefore, Q is 0. If Q is 0, ultimately we get E is 0. On that day, we discussed that at an internal point of hollow charged body, from the Gauss's law, the electric field intensity is 0. So this is also the mathematical proof of that particular experimental observation that inside the charged body there is no electric field. During the property of electric field lines, we say that there is no field lines inside the charged body, or electric field lines cannot form closed loop. Why it cannot form closed loop? Because inside the charged body there is no electric field. The mathematical proof is this. Okay. But what is electric potential at internal point of the hollow charged body? We already know that V is equal to minus dV by dx. We already, E is minus dV by dx. Can you remember it? E is equal to minus dV by dx. We had minus dV by dr likhichu. Inside the charged body, electric field intensity is 0. That means minus dV by dr is 0. Since dV by dr is 0, so numerator dV should be 0. What is dV? Change in potential. There should not be any change in potential. What is dr? dr is the displacement from surface to the internal point. When I move the test charge from surface to the internal point, what is displacement? Displacement is dr. During this displacement, there should not be any change in potential. Therefore, dV is 0. But what is dV? dV means Vi minus Vs. Vi minus Vs 0. Vi is equal to Vs. What is Vs? 1 by 4 pi epsilon 0 Q by R. That means at an internal point of a hollow charged body, potential is constant and its value is equal to the potential at the surface of the charged conductor. but inside the hollow charged body, electric field intensity is 0. Okay? Okay? So, if we graphically express the variation of electric field intensity with distance and electrostatic potential with distance for a hollow charged spherical body, then variation will be like this. So this is the variation of intensity. Inside the charged body there is no electric field. But inside the hollow charged body, potential has a constant value, and that value is equal to that on the surface of the potential. Okay, at external point, intensity varies 1 by r square and potential varies at 1 by r. Okay, so this is very important. Okay, so next we are going to discuss equipotential surface. The name itself said that equi means equal, potential surface. I mean, on this surface at every point electrostatic potential has the same value. Electrostatic potential has the equipotential surface, means this is the locus of the point in 2 dimensions where electric potential has the same value. What is work done in order to move the charge from A to B? Last class আমি পাইছিলো, it is Q0 VB minus VA. Since the potential has the same value, তাহলে VA is equal to VB. That means what is the work done to move the charge from A to B on the same equipotential surface? Q0 V minus V. গতিকে মোৰ work done to তোমাৰ কিমান হ'ব? 0 হ'ব। কাৰণ work done এক্সপ্ৰেছনটো কি আছিল? WAB is Q0 VB minus VA. এইটো লাষ্ট ক্লাছত আমি ডিছকাছ কৰিছোঁ। On the same equipotential surface, VB is equal to VA. So dV is, গতিকে W কিমান হ'ব? W Q0 V minus V is equal to 0 হ'ব। That means that no work is required to move the test charge Q0 from one point to another on the same equipotential surface. This is one of the characteristics of equipotential surface. The other characteristics is, what is dV? dV is equal to E dot dr. E dot dr means ki dW by Q0. It is from definition. Since on equipotential surface dV is equal to 0, equipotential surface means ki at every point on the surface potential has the same value. At every point on the surface potential has the same value. So what is difference of potential between any 2 points? It is 0. That means ki E dot dx is equal to 0. E dot dx 0 means ki theta cos theta must be 0. So theta is 90 degree. Theta is 90 degree means, that means displacement is on the surface. Electric field on the equipotential surface should be normal. Electric field on the equipotential surface should be normal. Because this is the displacement dx. Okay, this is the equipotential surface. I move the charge Q0 from here to here. So this is dx. So this is electric field. What is the angle between them? Angle between them is 90 degree. That means on the equipotential surface, electric field lines must be normal to the surface. Because electric field must be normal to the equipotential surface. There is another property, there is a property number 3. There is another property number 3. What is E? E is minus dV by dr or minus dV by dx. What is E? E means minus dV by dr or minus dV by dx. On the same, okay, between 2 equipotential surface, dV becomes constant. Say I have 2 equipotential surface. So what is difference of potential? It remains constant. That means dV is constant. E inversely proportional to dr. That means dr inversely proportional to E. That means if in the region electric field is strong, dr should be less. Or if electric field is weak, dr should be high. That means from the separation of 2 equipotential surface, we can make certain conclusion about the electric field. for the strong electric field region, for strong electric field region, কি দিছে separation between two equipotential surfaces decreases. তাৰপিছত দিছে for weak electric field region, separation between equipotential surface increases. This particular concept can be explained from the next experimental point, that is the point number 4. For a point charge, what is potential? 1/4 pi epsilon 0 q by r. That means if the origin of the electric field is a point charge, then equipotential surfaces are কি spherical হ'ব. ইয়াত মোৰ আকোতে পুৰা স্ফিয়াৰ হোৱা নাই, তোমালোকে ভালকে আঁকিবা, স্ফেৰিকেল হ'ব. এতিয়া চোৱা, ইয়াৰ পৰা ইয়ালৈ ডিষ্টেঞ্চ r1, এই পইণ্টটোক মই কিউ চাৰ্জ বুলি কৈছোঁ. চ' এইটো পইণ্টত পটেঞ্চিয়েল কিমান হ'ব? v1 = q by r1. মই কনষ্টেণ্টটো কোৱা নাই. ইয়াৰ পৰা ইয়ালৈ ডিষ্টেঞ্চটো r2. চ' এইটো পইণ্টত পটেঞ্চিয়েল কিমান হ'ব? v2 q by r2. ইয়াৰ পৰা ইয়ালৈ ডিষ্টেঞ্চ r3. ইয়াত পটেঞ্চিয়েল মই কিমান কৈছোঁ? v3 কিমান হ'ব? q by r3. ইয়াৰ পৰা এইটো ডিষ্টেঞ্চ মোৰ r4. চ' ইয়াত পটেঞ্চিয়েল মই কিমান কৈছোঁ? v4 কৈছোঁ. v4 is q by r4. From the figure, it is found that R1 is less than R2, R2 less than R3, R3 less than R4. Therefore, V1 greater than V2 greater than V3 greater than V4. That means as we move away, potential gradually decreases. And this is one equipotential surface. This is one equipotential surface. This is one equipotential surface. And this is one equipotential surface. In order to move a charge in this surface, no work has to be done. In order to move a charge, no work has to be done. In order to move a charge on this surface, no work has to be done. In order to move a surface here, no work has to be done. But which one is higher potential? This is higher potential. Potential gradually decreases. You just see the separation between two surfaces. You just see the separation between V1 and V2, separation between V2 and V3, separation between V3 and V4. So separation between V3 and V4 is more than separation between V1 and V2. That means electric field here is weak. Electric field here is strong. Yes, it is true. Because this point is close to the origin of the electric field. And this point is away from the origin of electric field. So here electric field weak, here electric field is strong. Since electric field is strong here, equipotential surfaces are closer here. Weak here, so equipotential surfaces are separated here. Is it clear? That means for a point charge, equipotential surfaces are concentric spherical surface, but as the distance increases, separation between two equipotential surfaces also increases. In order to move a charge from here to here, no work has to be done. But if you want to move a charge from this surface to this surface or this surface to this surface, you have to do the work. If you want to move the charge from here to here, if you want to move the charge from here to here, here to here, here to here, work has to be done. Because this and this, they are equipotential surface, but they do not have the same value. সিহঁতৰ ভেলুটো একে নহয়। এইটো সাৰফেসত মুভ কৰিলে ওয়ার্ক কৰিব নালাগে, এইটো সাৰফেসত মুভ কৰিলে ওয়ার্ক কৰিব নালাগে, কিন্তু ইয়াৰ পৰা যদি ইয়াত নিয়া বা ইয়াৰ পৰা যদি ইয়াত নিয়া ওয়ার্ক কৰিব লাগিব, ইয়াৰ পৰা ইয়াত নিলে ওয়ার্ক কৰিব লাগিব। বুজি পাইছা? এইটো ক্লিয়াৰ হৈছে? That means for a point charge, equipotential surface is concentric spheres. Next we try to draw the equipotential surface for two like charges. So these are the two like charges. This is positive, this is positive. You just see the separation between the surface. Here you see the separation gradually increases. Why? Because for two like charges, electric field is weak in between the two charges. At the end, field is strong. So therefore, equipotential surfaces are crowded here. But you just see the separation. You see the separation from here to here, from here to here, from here to here. Or from here to here, here to here, here to here. Okay? Clear? But another important point in this case, during the study of lines of force, electric field lines, for two like charges, we say that this point is zero electric field. But this point is not the zero potential field. এই পইণ্টত কি আছিল? ইলেক্ট্ৰিক ফিল্ড জিৰ' আছিল, কিন্তু এইটো পইণ্টত ইলেক্ট্ৰিক ফিল্ড কিন্তু ইলেক্ট্ৰিক ফিল্ড পটেঞ্চিয়েল কিন্তু জিৰ' নহয়। এইটো পইণ্টত ইলেক্ট্ৰিক ফিল্ড ইণ্টেনচিটি জিৰ' আছিল, কিন্তু এইটো পইণ্টত ইলেক্ট্ৰিক পটেঞ্চিয়েল কিন্তু জিৰ' নহয়। সেইকাৰণে চোৱা দুইখন ছাৰ্ফেচ ইয়াত অলমষ্ট টাচ কৰিছে। Equipotential surface never intersect each other, but they touch at this point. Why? Because potential of this surface and potential of this surface exactly same. At a point, exactly at the midpoint of two like charges of equal magnitude, electric field intensity is zero, but electrostatic potential is non-zero. Is it okay? Next, we want to draw the equipotential surface for two unlike charges. This is positive charge, this is negative charge. Okay, you just see equipotential surfaces are crowded in between the two charges. Why? Because electric field is strong here. And at these two ends, you just see equipotential surfaces are separated. Why? Electric field is weak here. Okay, now you just see the separation. This separation is small, this separation is large. Why? Because as I move away, electric field decreases. Here also, you just see the separation between two surfaces. As I move away, electric field decreases. So this is the equipotential surface. This is the equipotential surface for two unlike charges of equal magnitude. Unlike charges of equal, charges are unlike but their magnitudes are same. But if you see in this particular situation, I draw a dotted line exactly passing through the exactly midpoint of the two charges. So along this line actually represents the zero electric potential. A line to কিন্তু তোমাক কি দিব? Zero electric potential দিব। কিন্তু ইয়াত কিন্তু electric field zero নহয়। আমি পঢ়িছিলো lines of force. When the charges are unlike charges, at the midpoint, electric field intensity, when the charges are unlike charges, at the midpoint, electric intensity is non-zero, but electric potential is zero here. Okay, is it clear? Next we try to draw the equipotential surface for a uniform field. Yes, so uniform field of কি হয়? Lines of force black straight হয় আর equally spaced হয়, separation to চোৱা। So এইখন এখন equipotential surface, এইখন এখন equipotential surface, এইখন এখন equipotential surface. That means for a uniform electric field, equipotential surfaces are plane surface, and you just see the separation between the surface. They are equal. But this is a different equipotential surface, this is a different equipotential surface, this is a different equipotential surface. If you move the charge on this surface, or on this surface, no work has to be done. But if you want to move the charge from here to here, you have to do the work. Here to here, you have to do the work. Okay? Now, I want to discuss one of the very important characteristics of equipotential surface. We already discussed that two electric field lines never intersect each other. Similarly, two equipotential surfaces never intersect each other. If they intersect, what happens? We may draw two normals. I think in the second property, in the property number 2, we say that the electric field lines are normal to the equipotential surface. If two equipotential surfaces intersect each other, at the point of intersection, we may draw two normals, and that two normals gives two values of electric field intensity at a point, which is not possible. Therefore, two equipotential surfaces never intersect each other. So, today we are mainly studying some of the basic characteristics of equipotential surfaces. মই এবাৰ ৰিপিট কৰি দিব বিচাৰিছোঁ. What is the first one? No work is required to do to move a charge from one point to another on the same equipotential surface. Next important property to কি আছিল? Electric field lines are always normal to the equipotential surface. Next property to কি আছিল? Property number 3. For same difference of potential, for same difference of potential, if the field is strong, distance of separation between the two equipotential surfaces is less. Or if the field is weak, distance between the two equipotential surfaces is large. কারণ আমি কি পাইছিলো, for same potential difference dV, E inversely proportional to dr. তার মানে if the distance of separation between two equipotential surface is large, electric field is weak. Or if distance of separation between two equipotential surface is less, then electric field is strong. যে যিটো বস্তু আমি অলৰেডি এই প্ৰপাৰ্টিটোৰ পৰা আমি পাইছোঁ, ইয়াত কি আছিল, দুটা লাইক চাৰ্জৰ কাৰণে কি আছিল, মাজত ইলেক্ট্ৰিক ফিল্ডখন উইক আছিল। সেইকাৰণে চোৱা ইকুইপটেঞ্চিয়েল ছাৰ্ফেচৰ ছেপাৰেশ্যনটো চোৱা, ইউ জাষ্ট চি দ্য ছেপাৰেশ্যন বিটুইন দিছ ছাৰ্ফেচ এণ্ড দিছ ছাৰ্ফেচ, এণ্ড এইখন ছাৰ্ফেচ আৰু এইখন ছাৰ্ফেচ ছেম পটেঞ্চিয়েল আছে, পটেঞ্চিয়েল ডিফাৰেঞ্চটো একেই আছে, কিন্তু ইয়াত ডিফাৰেঞ্চ চোৱা, ইয়াত ডিফাৰেঞ্চ বেছি আছে, কিয়, ইয়াত ফিল্ডখন উইক, আৰু ইয়াত ডিফাৰেঞ্চটো কম আছে, কিয়, ইয়াত ফিল্ডটো ষ্ট্ৰং। আজিৰ ক্লাছটো আমি ইয়াতে ৰাখিছোঁ। আজিৰ ক্লাছত আমি মেইনলি ইকুইপটেঞ্চিয়েল ছাৰ্ফেচৰ প্ৰপাৰ্টিবিলাক ষ্টাডি কৰিলোঁ। থেংক ইউ, আজি ৰাখিছোঁ দেই ইয়াতে।